Hey everybody, Chris McClure here. Now here on statistics, we're going to continue talking about trying to turn data into information. And here in chapter 2, we'll talk about taking that data and organizing it. Now here in section 2.1, all we're simply doing is just talking about some characteristics of data that we will be looking to uncover as we go through our analysis of our data. We'll be looking for some sort of measure of central tendency, as in finding some number, some representative value that shows us what is that most likely value, or if you were to arrange that data from smallest to largest, maybe what is that one number that somehow represents that middle. Also, we'll be looking to find some measure of variation. In other words, how spread out are the numbers in relation to the center. We'll be looking to characterize the distribution. We could describe the distribution by talking about the shape of the graph of the histogram, for example. We'll talk about what histograms are later on. Or in the case of continuous distributions, what is the shape of the relative frequency chart for the entire population? Well, if we can see what it is for the data, then that will give an indication as to what the distribution is for the population. So what is the shape of the chart? Are we looking at a bell-shaped sort of distribution? Are we looking at a unimodal sort of shape, a uniform where it goes straight across? Or is it skewed where there's a hump on one side with a long tail toward the other side? So we'll be talking about these different types of distributions later on. We're curious to know, are there any outliers? And then what is the significance of any outliers? And briefly, what an outlier is just a data value that is relatively far away from the main body of data. And then finally, if time is one of the variables in play, how is the other variable changing relative to time? So, for example, if we have data that measures height over time, well, for each individual, like for example, blade of grass or a person or whatever, they might have, for each day or each month or whatever, 2 measurements for each individual. Time would be one measurement, and height or length or whatever, some other sort of measurement for the other measure. And you could plot those data points with time on the horizontal. We'll be looking to see how is that one measurement variable changing relative to time. So we will look at that in the sections to come. Now what we're going to do is turn to section 2.2 now, and in particular we're going to take a look at taking your data set, focusing on quantitative sort of data, and taking that list of numbers and organizing it by creating so-called frequency distributions. So what is a frequency distribution? Well, it is a way of organizing and summarizing a large data set. So we're going to organize and summarize the data by constructing a table called the frequency distribution, in which we will create some intervals of equal length. and we will count the number of, well, numbers in your data set belonging to each interval. The good thing is if you have a huge data set, we don't really have to do it by hand. Well, I want you to know how to do it by hand for a smaller data set so you can understand the concept. But the good thing is if you've got several hundred or thousands or millions of numbers and you've got them on a spreadsheet or in a computer platform, statistical platform, with a couple clicks of the mouse, you can have the computer do it for you. And it'll still be important for us to use our judgment to be able to interpret that data, though. So here's kind of a definition of what a frequency distribution, aka frequency table, is. And I'll let you read that. So what we're going to do is we're going to create these categories or classes. In other words, these are intervals. So what we'll do is we will list these intervals and then count the number of numbers with tally marks maybe, or tick marks, representing the number of numbers in the data set belonging to each interval. So here's an example here. And you'll see the data set in your textbook when you open up to section 2.2 of, a bunch of IQ scores. Well, we can create these classes here. Class is another name for interval. So we'll call these classes. And each class basically gives a range of numbers between 50 and 69, 70 and 89, 90 and 109. Now, understand that all of the numbers in your data set are integers, so we don't have to worry about, well, what if there's a fraction, what if there's a decimal? No, we don't worry about that because we're dealing only with integers. So, notice, by the way, that these classes are all of the same width. We'll talk about the definitions in particular. But if you were to take the high number minus the lower number, you have 19. And that's important. For every one of these frequency charts is to make sure your classes are all the same size. And that all the data values are annotated in here. Meaning you see that there are two numbers in your data set between 50 and 69 inclusive. That includes 50, that includes 69, and any number in between. And there are 33 IQs between 70 and 89. There's 35 IQs between 90 and 109. 7 IQs between 110 and 129. There's 1 IQ between 130 and 149. So this actually gives us a lot of a nice summary. This gives us a nice summary. Now, let's pay attention to these lower numbers. These lower numbers for the classes are called lower class limits. And these upper numbers are naturally called upper class limits. Class boundaries, well, let's take a look. They typically will not be members of either the lower class limits or the upper class limits. Now, if you were to take a look at the difference between, say, this upper class limit of 69 and the next class lower limit of 70, halfway between 69 and 70 is 0.5. So that means 69.5 is that halfway point between the upper limit of the first class and the lower limit of the second class. So it's half a unit above and below. So that tells us that 49.5 is the lower class boundary, is that first class boundary to start off with. And then it's going to be exactly halfway between the upper limit of the one and the lower limit of the next one. So 89.5 is halfway between 89 and 90. And 109.5 for this boundary here, and so forth. And notice that the difference between each successive class boundary is 20, just like the difference between each of these lower class boundaries is 20 as well. It's going to have the same difference between the class boundaries as between the lower and the upper class boundaries, 20 in this case. Now the class midpoints will be basically the average of the lower and upper class bounds. So if you were to take the average of 50 and 69, you would get 59.5. All you need to do is just add up these two, the upper and the lower, and divide by 2. So 50 plus 69 divided by 2 is 59.5. 70 plus 89 divided by 2 is 79.5, and so forth. So these are your class midpoints. That number that's exactly midway between the lower and upper class limits. The class width will be the difference between two consecutive lower class limits, which is the same as the difference between two consecutive upper class limits, which is the same as the difference between two consecutive class boundaries. All the same, 20 in this case. So now that you see that frequency distribution chart that you see there, why would we do this? Why would we organize it? Well, they say that a picture is worth 1,000 words, right? This allows me to quickly see roughly what the distribution of those IQ scores are. We could see that there's a lot more clumping of the IQs in the 70 to 110 range compared to the 110 to 149. You can see that there's kind of a peak somewhere in the 90 to 109 range, and that tapers off beyond, as we would probably expect anyway. And then also tapers off toward the lower end as well. So we can summarize large data sets. I would much rather be looking at this than, let's see, how many do we have here? We've got 40, 75. Oh, hold on, let's add these up. 35, 70, 78. I'd rather be looking at this than 78 numbers. And 78 is a relatively small data set. So imagine having a huge data set. I would much rather be looking at that than that huge data set. You can analyze the nature of that data, looking to see where the peak is, for example, or is it roughly uniform? In other words, you can kind of characterize the distribution. We could talk about constructing various charts, like line charts or histograms, for example. So how do we create a frequency distribution? Well, I'll step you through it step by step. So how many classes should you have? Well, typically it's going to be between 5 and 20. I would recommend about 10. Doesn't have to be 10. Depends on how much detail that you want. If you've got a huge data set and you want some detail to it, I would say go closer to 20. If you've got a relatively small data set and you don't care about a whole lot of detail, then make it closer to about 5 or 6 or 7. So you decide. Once you decide on the number of classes, then to decide on your class width, here's a quick calculation that you could do. You can sort your data set from smallest to largest, pick out the largest number, pick out the smallest number, and subtract, largest minus the smallest number. That'll give you the range. And then divide by the number of classes. Okay? And you'll have to decide on a logical starting point, as in like the lower boundary of the first class. So you use some judgment. If the smallest data value as, say 21, for example, maybe choose 20 as the lower boundary for your first class. Make that lower boundary a little bit smaller. Now, if it's 17, then choose 15 maybe, or 10. You decide. And same thing for the maximum value. Have it go a little bit above that maximum value from the data set. So I'm talking about the upper class limit for the last class. Again, adjust accordingly. You want to be able to have your entire data set broken down according to the different classes. So once you decide on your lower class limit and using this class width, then you can, add the class width to each subsequent lower class limit. So if you have a class width of, say, 10 with a starting value of 10, so you will have lower class limits of 10, 20, 30, 40, and 50, and so forth. And then use logical upper limits. If you're dealing with just integers for your data values, then you can go from 10 to 19 for your first class, 20 to 29 for your second class, and so forth. And go ahead and list those upper class limits. And then once you've decided what all your classes are, then you can go through your data set. And this is really useful when you have your data set sorted from smallest to largest, and you can easily count the number of data values in each data set, or in each class, I mean. So that's what we're seeing right here. We saw in that data set for the low lead group, you'll see this in your textbook in section 2.2, that there were two numbers between 50 and 69 and so forth. So when you're doing counting, you could use tick marks, or you could just simply count 1, 2, write the number 2 there, and count that there are 33 numbers between 70 and 89 inclusively. So you could either use a bunch of counting tick marks here, or you could just write the number 33 and so forth. Okay? So we're talking about the absolute frequency. Now, a lot of times, though, you will want the relative frequency distribution. Well, relative frequency is where you take each class's frequency and divide by the total number of numbers, by the sum of all the numbers, meaning by the total number of numbers in your data set, which is going to be the sum of all your frequencies. And if you wanted to even convert those to percentages, then just multiply by 100%. The relative frequency will just be a decimal, or maybe a fraction if you want to do it that way. But the percentage, you can just multiply by 100%. So, for example, going back to the low lead IQ scores, if you add up the frequencies, I think you get 78. Then take each frequency divided by 78 and multiply by 100. And that's where you get these frequency values here. And if you did it right, when you add up these frequencies, you should get 100. But you're not always going to get a sum of 100 because of round-off error, but it should be very close to 100. Another little trick that you can do is to do the cumulative frequency. Now, the cumulative frequency is where you have this column that is right next to the frequency column, and then you go through and accumulate frequencies. So of course this first entry will be 2, same as the frequency. And the next entry will be where you take this 2 plus this 33 to get this 35. So this tells you that there were 35 individuals with an IQ score 89 or less. And then to get to this next entry of 70, you take this 35 plus this 35 to get 70. And this tells you that there were 70 individuals with an IQ score of 109 or less. And then to get to the next one, you get you add 7 to the 70 to get 77. This tells you that there were 77 individuals with an IQ of less than 129, or less than or equal to 129. And then finally, this last entry is 78, which should match the total number of individuals in the data set. There were 78 individuals with an IQ score of 149 or less. So that's why we call this cumulative frequency. It's constantly rising. It accumulates the frequencies in this column here. Again, what we're looking to do is try to characterize the distribution of the data set, which should then tell us, what sort of distribution that the population is that we took these data values from. So, for example, the low-lead IQ scores that we were looking at, let's go back to this. We could see that there's a bit of a peak here in this range of IQ scores, and it tapers off to the left and to the right. Now we would be expecting that if we had some sort of central peak somewhere in this neighborhood between 70 and 110, and that's evidence of a sort of of a normal distribution. There's many other sorts of distributions out there, but a normal distribution is one where you have a sort of bell shape, where there's a central peak and then it tapers off to the left and to the right. But there's many others that have a single peak, like a skewed distribution. So it's kind of tough to tell right now. This very well could be a skewed distribution, but we shall see, though. We're looking to see, generally speaking, what is that distribution of the data, which should be a reflection of the distribution of the population. But this is some things to look for as evidence for a normal distribution, in which, you start off with small frequencies in the lower value classes, and then you have a large number of, for a frequency somewhere in between, and then it tapers off again toward the higher part, and there's a sort of symmetry between the lower end and upper end. And also you are looking to see, are there any gaps? And when you see a gap, that's evidenced by this. Let me show you this, an example of a gap, where you have this frequency diagram, and where you have these frequencies for these classes that are not zero, and then you have a bunch of zeros here, one or more zeros, and then you've got some non-zero data right here. So this shows actually 2 peaks, which is evidence of 2 or more populations. But just because you have data from 2 different populations does not necessarily mean that you're going to get gaps. So just understand that. So this is the example. Suppose that we take a random sample of pennies from the store that you've been running the cash register for at the end of the day. Well, it turns out that for the U.S. Mint, that pennies made before 1983 are 95% copper and 5% zinc. They have more copper content. I happen to know of a couple of individuals who are actually collecting pennies made before 1983 because they're supposedly more valuable. Anyway, and then it turns out also that pennies made after 1983 are 2.5% copper and 97.5% zinc. So suppose that you weighed each penny in your sample, and then here's your frequency chart for the weights of all your pennies. So how many pennies do we have? We have 37, 39, 64, 72. We got 72 pennies. And again, you see this gap. So that's evident that you have pennies from two different groups, two different populations. Okay, so that is the how we made a frequency chart from a data set, kind of in a nutshell, and some various things to look for. You're looking to see, what sort of distribution. Normal distribution is nice, but you're not always going to have a normal distribution. All right, but we will get to know and love the normal distribution if you don't already know it. So that is it for today. I've got homework posted, and I'll be posting section 2.3 tomorrow. All right, folks, have a good day, and I'll see you next time.